Do we have Dan? Great. So I have the pleasure of introducing our keynote speakers, Dan and Jeff. Dan is the Dean of the MIT Schwarzman College of Computing, and he has a mix of academic and industry background. He helped found the Cornell Tech and served as its first Dean and Vice Provost. He was also a researcher and manager at the Xerox Palo Alto Research Center and the CTO of a fintech startup. His main research areas include computer vision, social media, and understanding AI, and he's the co-author of the book Bruce mentioned earlier, The Age of AI and Our Human Future. And talking with Dan today in our keynote is Jeff Wilke. Jeff's an MIT LGO 93 grad and is the co-founder of Rebuild Manufacturing, a company looking to revive US manufacturing leveraging new technology. He hopes to create thousands of jobs in factories across America. Prior to Rebuild until 2021, Jeff was the worldwide CEO of Amazon Consumer, and during more than his 21 years at Amazon, he was the corporate officer and led Amazon's retail and third-party stores, fulfillment, logistics, supply chain, marketing, prime, and technologies teams. Prior to Amazon, he was vice president and general manager of pharmaceutical fine chemicals at Allied Signal, which is now Honeywell. So join me in welcoming Jeff and Dan, and we'll also have a brief video from Rebuild, one of our sponsors.
The engine that powers the U.S. economy and helps communities flourish. And we at Rebuild are wholly committed to its success. We're doing this by bringing together manufacturers that make quality products with companies that have technical and engineering proficiency. Now, together, as a Rebuild company, they're collaborating to develop unique production processes and manufacture innovative products that add even more value to a customer's business. To help companies that are here and those that want to reshore. Welcome home from Rebuild.
Hey, Dan.
Hey, Jeff, how are you? I think they were going to put you on that monitor in front of me, or otherwise I'm going to be going like this. Can the video get to the front monitor? Good to see you.
Yeah.
Welcome virtually to MIT. And
thank you. Did you notice? So I have this habit of putting the wall that you can't see is filled with albums, LPs, and I rotate them from time to time. In the most prominent position, I put one that might resonate with the location and with a few folks who are more in our generation.
I heard a few claps in the audience there, so I was encouraging them.
Okay.
So super to see you. Thanks so much for joining us. We had a chance to catch up a little bit a few days ago, which was great. Just watching your little Rebuild Manufacturing video there, if there's anybody who can drive the renaissance of manufacturing in the United States with a more computing technology savvy and driven way of doing things, you're the man. So really exciting to see that.
Well, we've got a great team. There are a bunch of MIT people involved. My co-founder, Miles Arnone, has been a terrific partner. Bruce has been involved from nearly the beginning. And as you know, there are lots of companies in the US that are already making things. So we're not the only ones. What we're trying to do is just help to rebuild that tier of the supply chain that we've sort of hollowed out over the last 40 years. The idea that you're going to build cars, really complex things, cars, planes, power plants, new pharmaceutical processes, biotech, medical devices in the US without a tier of multiple tiers actually of suppliers who can do co-engineering with you, process and product development, kind of like the large cities and regions in China now, where you go to, if you want to do one thing, you go to a particular kind of product, you go to the city or region, that has the full stack of capabilities you need to develop the product and produce it. We've lost that in the US, and we're trying to sort of fill in some of the pieces that are missing, especially on the technology side. And we have the capability to produce for our customers too, if they need that.
So as a, CS and AI guy, I always love it when people in manufacturing talk about full stack. I love the analogies that are now really moving back and forth between, different parts of industry and where the challenges of working with physical things is really changing how computing and, how AI is working, but also the flip side, how computing and AI, is certainly, as you led in your time at Amazon, completely transformed things like the warehouse and logistics businesses.
Yeah, the audience may not know that Dan served on the Amazon board for quite a few of the years that I was there, and it is funny, we would use these sort of software architecture metaphors in a bunch of ways. One of them is actually organizational design. We didn't talk about this, before, but as we were preparing for this, but the idea that APIs in 2002 or 3 completely unlocked software development, especially among different organizations that were collaborating at arm's length. We sort of tried to build that into the way we designed our organizations, where you would have separable teams working on very specific things that you tried to have them only communicate through very well-defined interfaces, as opposed to requiring armies of program and project managers to coordinate a very complex matrix. And that sort of helped us scale. I wonder what other analogies from the software world are going to sort of diffuse into our, there's a chemical engineering term, sorry, but diffuse into our organizations and things like mechanical and electrical engineering and so on.
Yeah, no, I've certainly learned a huge amount being on the Amazon board about organizational structure, and I love that analogy. So maybe on the topic of diffusion, diffusion's actually become quite relevant to machine learning these days. Probably something that's on many people's minds in this room, I would wager, is, how are all these rapid advances in machine learning really standing to affect, operations management at sort of all levels of the stack, and sort of how do you see that? How's the technology evolving? Maybe we could sort of dive a little bit into that topic area.
Yeah, that sounds great. I found it interesting that the acronym that we use for this part of MIT, is MIMO, which of course is machine intelligence for manufacturing and operations, but also multi-input, multi-output control. And the first time that Bruce used the term, I sort of went back to I don't know if it's still there at MIT, the graduate course called MCS1, Multivariable Control Systems 1. If there may be some folks looking at you right now, Dan, with a pained look on their face. I
see Dwayne Boning smiling.
Yeah. Well, Dwayne's smiling, of course, because it was a weed-out course. But that course, the idea that you have multi-input, multi-output systems in a whole host of areas, complex things like flying a plane and petrochemical plants and so on, is for me is a really interesting way to frame the different levels and aspects of an architecture that we're moving toward in manufacturing operations and in other realms. And so we talked a little bit about this up front, but maybe we can sort of drill into what are some of the key aspects of a multi-input, multi-output control system, and then how does that relate to the way AI is diffusing into the org. So, what I learned from that, the frameworks in that course were that, you've got first order problems of observability and controllability in these large systems. And this is true for what we're trying to do in manufacturing. We need to be able to, in order to tune whatever models we're using, whether they're human-based or machine-based, we need to have the ability to observe what's happening, what humans are doing as they work with machines, what the machines are actually doing at a nano level, a micro level, a milli level, and an aggregate level. And that's a function of the sensors we install. I mean, right now, in the absence of perfect sensing, as you know, we rely on the sensors that humans happen to have built into our biology. And those sensors have allowed us to make great progress for a lot of years, but they have a certain speed, which is limited by our 60-watt brain. And the ability to augment those sensors with machines, to me, is of great value, especially in this world where, and I think we're going to talk more about this, where we're increasingly using proprietary data sets to enhance the performance of large language models. And then you have some state space model that your controller is operating on in a MIMO control world. And you reminded me that when we talked that, I would have thought about writing the state equations in time domain and then use Laplace transforms to turn them into a state space model. And it turns out modern machine learning allows you to have implicit representations of state in addition to explicit ones that I would have thought about, in the past. And that's a whole area that we'll talk in a lot more detail about today, I think, because those models are going to be critical to improving the performance of the control systems. And then actuators are, in the classic sense, are humans with dumb machines. And increasingly, I think we'll move to a world in manufacturing where the actuators are a hybrid of human actuation and a lot of machine actuation that's much more intelligent. And the great benefit, of course, there is that we get to move to a world where we're not dependent on reinforcement learning with human feedback that's human paced, but we can actually get reinforcement learning to be closed loop with machines learning from the machine actuation. And that's where we come up with all kinds of data that we haven't had in the past. And some of that data will not be intuitive to the humans that are looking at it, but that's the whole point, right? Is that we can explore parts of the state space that we weren't able to explore before. So, and that's the framework that I've been thinking about is back to something that we who have worked in operations for a long time or who are studying it for the first time really understand, which is the math and the frameworks behind closed loop process control. And every single piece of that framework is being impacted, in enormous ways already by AI and large language models. And I can't imagine, kind of what's to come. But I know, Dan, you've been thinking about this for years, well before me, as is often the case when I talk to Dan. He's already got a mental model as I'm still forming one. But Bruce, I think, had mentioned the age of AI in our human future, which you wrote with Henry Kissinger and Eric Schmidt. And maybe take us back to that for a second and just, maybe help us trace the arc of development of machine learning toward LLMs over the last 10 plus years in your framing of it. Because I think some of the insights that you built into, I could tell which of the chapters, actually one of the games I played when I read the book is to try to figure out which chapters you wrote. And I think I was pretty close, but you did it. I think you do a great job of pulling out the key insights and creating a narrative arc. Do you just help us sort of trace, how we got here?
Yeah, I'm going to actually start even further back in the technology realm than stuff we talk about in the book, because I just think that the sensors, state space, actuators, formalism, representation, mental model, you can use it in all kinds of ways. It can just be an abstract mental model. It can be, a bunch of mathematical equations that you write down. It can be a representational structure implicitly in some sort of, large scale AI and machine learning system. I think that's extremely powerful. And when we talked the other day, it sort of reminded me how much that's driven the ways that I've thought about AI since I was a grad student at MIT in the 1980s. I worked first in speech recognition and then in computer vision, so I was very much on the perception side of these things. And I sort of, found much of the work in kind of mainstream core AI at that point kind of frustrating. because it wasn't dealing with what I would say is really sort of the inherent uncertainty of sensory systems. Sensors, some of it's all the way down to the physics, like if you're counting photons in low light, there's just a lot of uncertainty there. But also with just the interpretation of what's going on in a complex world. And so I think one of the huge advances we've seen with machine learning over the last decade or so is the capability of dealing with a lot of that uncertainty and complexity on the sensing side. And then, of course, there's analogous complexity on the control side, because no control system really does precisely what you tell it to do, including, our human body when we think we're telling it to do something, and the muscles do something else. That's maybe, most evident, if you're doing something like playing competitive sports, you just like, how could I not hit that ball? So I think that those uncertainties on both ends are inherent, and whatever representational schemes we use in the middle need to sort of explicitly capture that and do a powerful job of representing that. And the traditional sort of formal approaches to this do that, but often then with things like a Bayesian statistical assumption. There's usually something built into the model that's sort of a guess of what the characteristics of those sensors and actuators are. And I think the big advance in machine learning lately is, as you said, it's essentially these implicit representations. But implicit representations that can sort of do three things that we do highlight in the book. It's that they're imprecise, they're adaptive, and you can get emergent behaviors out of them. And that really is, those three properties characterize what we tend to associate with human intelligence, and not with machines, right? Machines, very rigid, brittle. You think about conventional algorithms. It's, if you got anything slightly wrong, it just kind of blows up. And then I think that really focuses us on, from the engineering perspective, on, how do we really do a good job of training and those implicit representations? How do we get a good understanding of what those implicit representations are really capturing? But I think this is a fascinating, amazing new world for, everybody's looking at it from the large language models point of view, but I think, in the manufacturing domain, it's extremely important. I mean, I know, in the time that you were the latter part of your time at Amazon, a lot of those kinds of things, not LLMs, they weren't around yet, but a lot of machine learning was starting to be used really significant ways in the fulfillment system. And has those same characteristics, right? You've got both human and machine actuators in a large, complicated fulfillment center. You've got human and machine sensors. You're trying to, it's an incredibly complicated control system. You're trying to get some representation of it. So I think it really applies in all kinds of places beyond LLMs. And I can come back to the book if you want, but I want to stop and let you weigh in for a minute, since I started in a place much more closely tied to the sort of state space, sensors, actuators view of the world. I just think it's extremely powerful.
Yeah, it's interesting you bring up what we started to see together in the last couple of years that I was at Amazon, and it actually traces back to I think the time frame you were thinking about as we were learning the power of these new models, and you rattled off a couple of different domains, including Bayesian and others. And I think about 2012-ish as the inflection point. And what I started to see, I had a team that was small at that time, working on machine learning applied to a whole bunch of different places. And Amazon, of course, is not manufacturing in all of its realms. It is a manufacturer in terms of the electronic devices that it makes, but a lot of the way that we put the logistics world together actually resemble assembly processes. There's just not a chemical or physical.
Gee, I wonder why, because who led that?
Hey, in '99, I had one playbook, and it came from MIT, and thank God it worked. But so you fast forward to 2012, and we have all these applied math frameworks that are built into decision making and kind of the support for humans. And we had these teams of machine learning scientists starting to do A/B testing, king of the hill, against different kinds of of machine learning and AI. And 2012 is kind of the moment where they started to win. And then, year after year, more and more of the decision support and control systems that we had throughout the whole stack started to be replaced. The traditional algorithms replaced by algorithms in the realm of machine learning and AI, to the point where when I left, the preponderance of decisions were being made by, algorithms that we wouldn't have been able to write in 2010 or so.
Yeah, it's interesting. Oh, sorry, go ahead.
Sorry, go ahead.
I was going to say that sort of phase change in my mind, and I really think of it as one where, leading companies that had the expertise kind of switched off what they were doing and switched on machine learning in place of it. I peg that date at about 2015. It's when Google transitioned the search engine from sort of classical information retrieval algorithms to machine learning algorithms. They were doing exactly the same sort of things of sort of, A/B testing the machine learning against their classical methods and starting to really see that, it was, even if there was some uncertainty compared to what they were doing before of a different form. There was uncertainty in the algorithms they had before also. They got comfortable with that because of the performance switch. But I think it probably really was sort of, plus or minus 4 years around 2015. And, you all started pretty early on that, partly because of the preponderance of both data and growth in what you were doing. And with physical systems where you just had to start doing something else or you couldn't get the packages out the door, literally. Yeah.
And the fact that we had built, kind of a bias toward using algorithms instead of heuristics. Heuristics are algorithms too, but sort of more, state space driven algorithms, which lent an easier transition, I think, to ML and AI. One of the things that I found interesting when you were talking about the fundamental errors in measurement, in actuation, even in the state space models. One realm that we talked about before was anomaly detection. And I know this is one, I know you spent a lot of time thinking about this, as a grad student, and you tend to notice these kinds of, stochastic and error effects in systems as we've worked together. There's a bunch of work that's happening at MIT in this area, right?
Yeah, I mean, so one thing that's happened with the incredibly rapid advances in proliferation in machine learning, and both in sort of what I'll now call sort of classical kinds of prediction problems, and the generative sort of models. Is literally, it's more than a full-time job keeping track of everything that's going on. And so, but I'll highlight a few things that I think are particularly relevant here, that are very recent. So one thing is as you start to build these implicit models, which we're seeing sort of the consequences of in the large language models in a very sort of visceral way. The whole problem of what gets referred to in machine learning often as representation learning is extremely important. That is, if you sort of just turn these algorithms, these learning algorithms loose on big piles of data, you can get some sort of behavior out of that, and you can start to measure the behavior. But how do you really direct the training and direct the learning? And direct it in ways that your representations might have properties that you're trying to get. So, we've all sort of seen with large language models lately the use of RLHF, reinforcement learning with human feedback, which is, it's just amazing how A/B testing shows up everywhere. So, for those of you who don't know the details of RLHF, basically you take a large language model, you give it a prompt, and instead of having it give back the most likely response, which is what it's normally doing when it's interacting with a user, it gives back 2 responses, and a human being's supposed to say, this one's better than that one. Literally A/B testing. And you can sometimes do this with a small number of responses and rank them, but people are better at A/B than they are at ranking things. So that kind of feedback is what you were referring to, that just sort of doesn't scale because it's human input on these things. And so a lot of representation learning is looking at automated ways in which you can manipulate your training data to try to get properties of the implicit learned representation that you would like to see in the eventual system. And I think this is an extremely important area, and everybody should know about it because it's so relevant, both to these sort of sensing and controls things, but to sort of everything that we do with machine learning. And since I'm a computer vision person, I'll just give you a really simple example that's easy for me. So if you think about a collection of images, and maybe you're trying to do something, like do object recognition from those images, there's lots of variations in the ways things can appear in images that may not be well represented in your training set, and you'd like to sort of have the representation that your machine learning algorithm learns be sort of invariant to certain kinds of things. So you literally can just take your input data and do things like do rotations or do affine transformations, or you do transformations that even if they're not accurate, like the cats don't appear upside down very much, so maybe you shouldn't, but you do this and you just sort of rotate the pictures in all orientations, you get representations that perform much better under the kinds of real variation that you see in the input data. So that's just sort of an example of how you do sort of artificial transformations of the input data that are aimed at certain kinds of ways of making the representation, say, more invariant to things that might not appear enough in your training set. And I think you can imagine in almost any context where you have, sensory data that there are some variations that you really want to be sure that the representation doesn't get tripped up by. I think we can think of really bad versions of that, like, the airspeed sensors in modern airliners, and there's a certain kind of unreliability that they have that hasn't been that easy for traditional digital control systems to do a good job of responding to, and, sometimes they don't hand it off to the pilot all that well, and we've actually seen crashes in the last 15 years or something, based on those issues. But those are things where that's a property of the sensing system that we know about abstractly, that you're not going to see very often in the training data. But when it happens, it's something you really have to be sure that your implicit representation knows how to handle. So it's sort of these kinds of aspects to the training that I think are super important. So anyway, that was a little bit of nerding out, but Jeff and I.
Yeah, we used to do this at board meetings too. So we should just do a blanket apology and then keep doing it because it's fun.
Yeah, we'd get chastised by the board chair. Hey, you guys need to come back in the board meeting. Stop that.
So, this leads me to think about how quickly our understanding of this whole space and, kind of writ large is changing. Everything from how much it's going to cost to build the models, how many LLMs will there be, and if people extrapolate that to, AGIs, how many of those are there going to be? What happens when all the public tokens are trained on? And, so I think about the last 6 months. 6 months ago, I was having conversations with people that are experts in this field. And the debate was kind of like, are we going to have 2 or 3 LLMs that basically become AGIs at some point? And that seemed to be, not for everybody, but for lots of folks, that was kind of the consensus, that we were heading toward that kind of a world. And then all of a sudden, you basically see the difference between 3.5 and 4.0, and you look at some areas where there were huge leaps in performance, but other areas where we kind of trained on all the public tokens. And, we'll keep adding more tokens, but we're not going to see the kind of super linear or crazy, performance improvements perhaps that we've seen in the last couple of years just from using public data and training, non-domain specific LLMs. So this idea that there are ways to speed up the reinforcement learning using proprietary data sets, I think is super interesting in the manufacturing space. Because now fast forward 6 months from 6 months ago, and the conversations that I've had in the last month or two are about the power in using these proprietary data sets to do the kind of domain-specific training and tuning that's going to be necessary to, for example, in manufacturing to succeed. Maybe 6 months or a year ago, there would have been popular articles written about how, LLMs, or it would have been 6 months ago, LLMs are going to be able to run our factories and, not only drive our cars, but run our factories. And we've seen with autonomous vehicles, this goes to your point before about how much data you actually have to train on, especially in the tails of experiences that the system's going to have to be prepared for in order to make it robust enough to trust it completely. And that's a place where we have millions and millions and millions of data points per minute coming in, because of all the cars that now are sending data to the cloud. We don't have that same kind of instrumentation and data streams in most manufacturing operations, certainly not providing data into any kind of a public corpus. So, how are you thinking about this sort of speed with which we're going to be able to get the generalized LLMs to be, tuned again, using some of the representation learning ideas that you just talked about, but to be really tuned to where we could walk into a control plant in a complex petrochemical operation in, say, Baytown, Texas, and find that the AI is actually running the plant?
Yeah, so it's an amazing set of questions there. I'm going to try to tease apart some aspects to it.
Sorry, that's like when I used to do investor relations, and the people, and they had limited time or one question, so they'd ask like an 8-part question, and I'm trying to write them all down. Sorry
exactly. Well, no, but they're really intertwined aspects. So, so the book with Kissinger and Schmidt, which we wrote really 2 years ago now, because it came out in the fall of 21, but by the time it goes through the whole press process. And I have to certainly credit Eric Schmidt with being the one who really pushed us to say, there's a whole discussion and an example in GPT-3 there, and that was Eric saying, this stuff is going to be big. So I have to say, my crystal ball is not so good. But there was, not that I was against it, I just was like, yeah, this is kind of one of a bunch of random examples we could be using. Not so much, not with 2 years of hindsight. But the flip side of this is, I think, and you know Eric pretty well, and so he's probably one of the people you were referring to who believed in the handful of large models out there with a handful of large companies. And I never bought that because while I did see the resource issues as being something that could limit it, I've also just seen so many generations of technology where things that took a huge amount of resource, the resource demands got ameliorated or mediated in some fashion. And we're already starting to see that with the large language models and diffusion models and other such models in computer vision, is that there's armies of open source developers and researchers saying, we shouldn't be using up a significant fraction of the Earth's power supply training models so people can have inane chats with online chatbots. Instead, we should think about, how can we really, focus on much more efficient versions of these. And that's happening at, I think, a quite rapid rate. And also, the development of open source versions of these things is happening really fast. And I'll point to another domain that you know really well, I know you've been really involved with, which is the protein folding, the algorithms for taking amino acid sequences and being able to, develop, to predict the 3D protein structures. That's a place also where, for a very short time period, there was a very big, very well-resourced company that had a clear advantage. And, now it's all open source, like what all the scientists are using, and they're using this stuff all the time. And I know you were very involved with Baker's lab in Washington. That's what all the scientists are using now. So I do think that sort of early advantage and scale advantage is probably less of one than we thought at the beginning. And I wasn't sure it was going to go that way, but it just made me suspicious of making predictions about it being a handful. But I think that the data sources that are necessary to train these algorithms to do useful things are often not public data. And that's a place where there's huge opportunity, but I also would have a huge caution there. So I think most companies and most leaders are not well positioned to be a digital-first company, and especially not to be an AI-first company. And I know this is what excites me about some of what you're doing when you work with larger corporations. You came to Amazon at a time that it was scaling like crazy, and it had a founder CEO who was digital first, and so that you were able to do that in that environment. But I think a lot of the companies that have access to the data today, are still stuck in some, last century version of digital technology, much less AI version. And back to the fact we were talking about organizations and organizational structure and organizational APIs, and I just think many of those companies are not well positioned to really start to use that data. And this is sort of beyond the kind of digital transformation that sort of comes out of how do you get really effective use out of an ERP system, and I mean those are super important too, and a lot of companies are in the middle of that transformation. But this is some different approach to leadership and management, and being willing to make investment risk, because these things are still not that cheap to undertake. So I'd love to turn it back to you with that set of flip questions.
Yeah, I see this all the time. It's in the manufacturing realm. Really sophisticated companies with terrific expertise in material science, electrical engineering, chemical engineering, mechanical engineering. And when I meet them and I'm disappointed in their software, forget about AI, just their software, their basic, software that's embedded in products or that's important to be able to use the product. I'll ask a simple question, which is, who's the senior most computer scientist? And we could extend that to be, who's the senior most AI or ML scientist in the company, and to whom do they report? And almost always in a manufacturing company, the answer to that question is shocking. It's usually, if it's computer science we're talking about, it's usually somebody who, is the CIO or CTO, but hasn't written code in a long time, spends a lot of time giving talks and conferences, which is great. This is super fun. But it's not nearly as important in terms of staying relevant if you're in that field than, writing code and getting your own human feedback for your own reinforcement learning on, how do I make the best of these tools? You and I were talking about, GitHub Copilot the other day, and I'm shocked at how improved the development of the first draft of code can be with the support of LLMs just writing out a first cut. But how do you have an intuition about how big that improvement is if you haven't written code before, if there's nobody at your side who's written code before, and you have to go into the CFO's org to find and love all the CFOs in the audience, but I don't think you want the senior most computer scientist in your organization in a manufacturing company to report to the CFO. You want to find somebody who is as senior as your best mechanical engineers, electrical engineers, whatever the engineering domain you're used to relying on for competitive advantage in your manufacturing company. You actually want to treat computer science and machine learning AI as equivalent to those. And that's kind of what we're doing with Rebuild. We've built an internal team of computer scientists. It's 30. We have 400 engineers in the company. So just under 10% of the engineers are actually computer scientists. And increasingly we're adding machine learning and AI, and not huge numbers of them, but enough that we can kind of tune the work of our computer scientists for some of the things that Bruce and his team are working on as we think about applying some of the large language models and other forms of ML AI into these manufacturing organizations that were small enough when we bought them. There's no way they would have had usually even a computer scientist, let alone an AI scientist, but now can take advantage of being part of an umbrella that includes more capability to apply across all these businesses. When I think about this, it leads me to how quickly, it's back to something I sort of mentioned before, but how long is it going to take before we have control rooms that run plants fairly autonomously without a lot of human intervention. The humans are there to really watch and catch anomalies that we haven't even seen yet. First of all, I don't know how you have that debate if you don't have a AI scientist or a computer scientist at the table at the C-suite when you're talking about your strategy. What plants are we going to build next year? How are we going to run them? What are we going to do to modify the ones we currently have? The one strange thing that, as I was thinking about this when you and I talked about it last week, is that I'm thinking back to walking into control rooms in large chemical manufacturing plants in the early 90s. And you would have, and I'm sure those of you who have worked in manufacturing operations have seen this before, you'd walk into a complex control room and there's, back in the day, there were screens, not really gooey, but, sort of screens all over the place and lights flashing and alarms going off. And people are sitting, together at a table chatting. And the first time as an MIT trained engineer, I walked in and I was expecting all this rigor, and I saw the scene. I was like, well, guys, there's alarms and lights, and why aren't you reacting to this stuff? And it's because they had learned that whatever the engineers had designed, the system had reached an equilibrium that they understood intuitively. And that gives me hope that we'll learn to trust the machine algorithms and their representation of state space over time, because we've learned to trust our own intuition, which is, has way less data and is ultimately less capable than the collective intuition that we're building today.
Yeah, so I think this raises a super important question about the sort of integration of AI controls and decision-making with human judgment. And, do we just defer to the automated one? Do we look at, because we don't understand much about how to even humans, take two people who have responsibilities, say, for something in a sort of emergency situation in a plant or, in a combat situation, or, how do they jointly make decisions quickly? Usually we just make one person the responsible entity and, it's on their shoulders. So I think there are really interesting questions about, how we start to roll out AI and machine learning decision-making, how we think about having humans in that loop, how we think about shared responsibility. Is that even possible? So I think, really interesting set of issues are going to come up there. But I agree with you. I think we will get to a world where these plants, you don't walk in and see a bunch of blinking lights and humans ignoring them. There's a system that is controlling this that has learned a lot about what's a safe operating set of parameters for the plant. So,
yeah,
so I see the little red light blinking in front of me here. So I should maybe give you a chance to say one last thing, but we should turn over to the next session.
Great. Well, there's one other topic that we didn't talk that much about, which the framers had asked us to, and that's sustainability and how these areas relate to it. And I just put a plug in. I was talking about chemical plant operation, and certainly our power generation and distribution is a key aspect of sustainability going forward. How we design that system. And if you've read, there's a Princeton study on kind of the U.S. grid that says we're going to need, under most circumstances that you could imagine, about 4 times the capacity than we currently have, which means we're going to get a chance to design a new grid. And I can't help but believe that AI is going to radically improve the performance, both of the design of that grid, because as we know, it's a very lossy system, with new ways to operate it, so that we can ensure that all of the power we generate is as efficiently as possible distributed. And that's, to me, those are the kinds of things you mentioned, protein design before. Those are the kinds of things where I think why I'm an optimist and why AI actually makes me even more of an optimist. I think there are giant human problems that we're more likely to solve with the assistance of machines than going it alone.
Sensors, state space, controls applies to the grid as well. And in fact, we've just hired some new faculty here at MIT who are bringing machine learning to bear in that space as well. Thank you so much, Jeff. Great to have you with us.
Thank you. Thanks, everybody.
Thank you guys so much. I think we actually have time for maybe 2 questions.
Oh, awesome.
If you want to stay seated.
Sure. Is Jeff still on? Yes.
Jeff's still on. Okay, great. Any questions in the audience for Jeff or Dan or both?
You got Jeff Wilkie here. You must have a question.
I have a quick one while people are thinking. My question is about how you apply a lot of these new technologies to maybe lower volume manufacturing. It's really obvious where a lot of these algorithms have applicability where there's a lot of scale, like Amazon benefited from that and rolling it out into their operations. But which ones do you think are most relevant to lower volume, maybe more complex manufacturing?
I'm going to turn that to Jeff. I do have a thought about low volume in general, but on the manufacturing context, let me first turn to you.
Yeah, it's a really interesting point because and you're thinking about sort of job shop type manufacturing, right? One thing that I just keep thinking about is using LLMs to help refine, basically to help survey all of the different ways people have approached particular problems, especially problems that humans are involved in. And coding is a great example of this, where you could just sort of start with a clean development environment, and you have some functional design and you start writing code. These days, you would actually type a prompt in, and you would get back source code that's a great starting point that actually is using all of the tokens that humans have put out into the world before you, and it's often not a bad starting point. I think the same thing's true in kind of job shop kind of environments. I mean, it's a better way to search for techniques that others might be using that you just don't know about.
Yeah, and I think just to build on that, I totally agree. And I think in general, the sort of what I'll call the manufacturability design stage, right? You go from some abstract customer need to something that you can actually make in the manufacturing environment that you have. Right now, that sort of design problem, if you're doing sort of low volume runs, your design overhead is very high for that kind of translation into the things that you can actually do with the equipment that you have. And this is, I think the opportunities for generative models to really help make design much more effective and efficient are huge. And so I think they apply here, but they apply, I think, really throughout, anytime you're changing a process, even in a big manufacturing setting, there's a design problem there. And I think LLMs and other generative models are going to be really, really helpful with that.
Just to riff on that, Dan, effectively what they do is they lower the activation energy or the minimum efficient scale that's necessary to be willing to use these things. Where in the past you would needed a giant plant in order to be able to afford to put a complicated control structure in place. Because the cost of these models is so much lower, you can do it for ultimately N of 1.
Yes, exactly. Yep.
Great, thank you. Any other questions? We'll bring the microphone to you. Thanks.
All right, this is more of an organizational question, but what are your opinions of having machine learning data science exist inside of an existing IS organization that maybe predates data science versus having kind of a separate organization versus having it decentralized into different departments throughout the organization? And maybe if you could talk about like the differences between legacy manufacturing companies versus your experience with Amazon, Jeff, and kind of the differences there.
Well, Dan, I'll start. My experience is that we were super fortunate, Dan kind of hinted at this, that we built a company that had operational capability right alongside world-class computer science almost from the beginning. And that proved to be hugely valuable as we were iterating on our kind of non-computer science designs. We had computer scientists right next to us who were like observing what we were improving and building, essentially encoding that learning into software so that we could ratchet our knowledge. It's kind of the way knowledge keeps accumulating in the human world, right? Where we, through writing first, and then encoding things in software and in physical instantiation, we get to stand on the shoulders of the work that's happened before us. So having computer scientists do that was hugely valuable. When we got to a point where we started to add AI scientists, I had this debate with a bunch of folks at the company, which is, do we create a separate team, which is where we started, or do we embed them in these individual teams? Now, we had long ago decided to have what we call 2 pizza teams, or very small teams that were focused on specific areas and dedicated to those areas. So we did not have a single IT team. We had a decentralized set of software development teams spread around the company that were very domain specific. That's the kind of environment that's ripe for dropping in some machine learning scientists into each of those areas. And that's kind of what we ended up doing, was pairing up people that knew these new algorithms with people that were maintaining in systems the existing algorithms, and magic happened. And I think we'll see the same thing even when you add LLMs. It's, computer scientists are well prepared to take advantage of advances in algorithms. And so when you take a high functioning software development team and you just sprinkle in a little bit of magic dust in AI, they get it pretty quickly. There's some pushback initially, that's not what I learned, not invented here kind of stuff. But when you see the performance improvement in the algorithms, unless you're a total obstructionist, you can't help but get on the train.
So one thing I would add there, I think, centralized information technology, information systems organizations are great when that's basically an infrastructure. But when it's something that is a competitive advantage, or when it's something that is, part of the core processes, you also wouldn't, if you're like a, chemical company, you wouldn't take your, you wouldn't have no chemical experts associated with the actual manufacturing operation. Like, you might have some research scientists in a central organization, but they're going to work closely with sort of research engineers who are deeply embedded with the actual operations. And I think, both to computer science and AI and machine learning, if you don't have that sort of structure, you can have some centralized people. But if it's all centralized, like most ITIS organizations are, that's great for support. It's not great for innovation. And I think that's consistent, I think, with what Jeff was saying. I just wanted to sort of broaden it a bit.
Yeah, and Dan, our answer is a little bit in the realm of very large companies. And the question was a good one about, kind of what do you do if you're not at that scale? And this is the advantage that we're seeing in Rebuild as we started by acquiring companies because we wanted to get moving fast. We bought 11 companies, and none of those 11 companies could have built, a 30-person computer science team or an AI capability on their own. And it's kind of interesting that while we're in this world where a person in a dorm room can create, a Dropbox, that doesn't work the same way in the realms of electrical, mechanical, engineering, material science, and the AI that supports them. You kind of need to have people together, at least under one, design roof, so that they can collaborate, quickly across across sort of technical boundaries. And so I would argue that there's a minimum scale where you're going to be able to kind of afford to do this. And really small companies are going to need to take advantage of partnerships with companies like we're trying to build with Rebuild and others who have this expertise, and where some of that expertise can accrue to the folks who just can't afford to do it at their scale.
Great, thanks, Dan and Jeff. It's been really enjoyable. Let's give them one more round of applause.
Jeff, as always, super to spend some time with you. Thank you.
You too, Dan. Thanks. Thanks, everybody.